So what you can see in front of you is known as a mapping diagram. And you can see on the left hand side we've got a set of numbers and they're referred to as the domain. So they're like the input numbers. Then in the middle you can see that what we're doing to these numbers is we're squaring them. And when we go and look on the right hand side, we've got the answers that you get once you squared each of those numbers in the domain. And those numbers are referred to as the range. So that's the output that you get. Now, a mapping is called a function if it's one-to-one. So that means that for every x value in the domain, there's a different y value in the range. So this graph demonstrates an example of a function. The other type of mapping that is a function is many-to-one. So this time there can be several x values in the domain that may all transform or map over to the exact same value of y in the range. So if you look at this quadratic graph, you can see how that happens. So there are I've marked out two values of x, but they have the exact same value of y. So that is a function. However, a mapping is not a function if it is one-to-many, i.e. there are more than one y value for every single x value. So you can see in this graph below an example of that. So for this x value here that we can see there are two y values, so that's not a function. The other way it's not a function is if there are just not y values for every single x value. So we can see on this graph that there are no y values, there's no part of the graph that's over here in this negative side of the x-axis, only on the positive side, and therefore that's not a function either. But sometimes you can turn a mapping into a function if you restrict the domain. So if we look at this graph of tan x here, every time we get to pi over 2, 3 pi over 2, of course we've got that asymptote going on there where there's no value, it's shooting up to infinity and down to infinity either side. So that doesn't fit the profile for it to be a function. However, if I take that same graph and I restrict the domain to between minus pi over 4 and pi over 4, this now is a function. Composite functions. So here's an example, f(g) of x. That's how they look. Now what this means is that we need to substitute the function g of x in place of the x in the f of x function. Now typically, 9 times out of 10, f(g) of x will not be the same as g(f) of x. It matters which way round you do it in most cases. Should you come across this notation, f squared x, then that actually means f(f)x. So in other words, you're going to substitute the function of x into the function of x. So we're going to look at how we deal with these composite functions, and the first method I'm going to show you can use if you're actually given a value of x. So for example, here we have f of x equals 2x squared minus 1, g of x equals x minus 5, and they're asking us to find f(g) of 2. So we've got that x value there. So the first thing we're going to do is evaluate g of 2, which would give us 2 minus 5, which is minus 3. Then we're going to substitute g2 into f of x. So that gives us fg2 equals 2 brackets minus 3 squared minus 1, which is 2 times 9 minus 1, which is 17. So method 2 is for when you're not given a value of x. So in this example, f of x is 2x squared minus 1, and g of x is x minus 5, and we need to find fg of x. So we're going to replace the x in the f of x function with g of x. So that gives us fg of x equals 2 brackets, put in the g of x, x minus 5 squared minus 1. Now we just need to expand and simplify. So expanding the brackets there, we get 2x squared minus 10x plus 25, and the minus 1 on the end. And if we tidy that up, we get 2x squared minus 20x plus 49. So just to show that g f of x is usually different to f g of x, let's do that. So this means putting f of x into g of x. So instead of the x in the gx function, we're going to replace that with 2x squared minus 1. And then if we expand the brackets, that leads us to 2x squared minus 6. So it's quite obvious that those are not the same. Now we're going to look at the inverse of a function. F to the minus 1 is how it's typically written. Now, only one-to-one functions have inverses. However, you can make some functions one-to-one by restricting the domain. So, for example, if we had f of x equals x squared plus 2, it would look like this on the graph, and you can see at the moment it's many to one. You've got two x values that have the same y value. But if we restrict it to just x is positive, we get rid of that side, and now it's only a one-to-one. So as is true with all inverses, f to the minus 1 of f of x will give you x, and vice versa, f of f to the minus 1 will give you x as well. So this is like taking away 2 will reverse adding 2. They're inverse operations. The domain of the inverse is the range of the original function, which also then means that the range of the inverse is the domain of the original function. So let me show you how to work out the actual inverse of a function. You're going to start by replacing f of x with y. Then you're going to make x the subject, and then you're going to replace x with f to the minus 1 x and y with x. So if f of x equals 4x squared minus 3, with the domain restricted to x is greater than or equal to 0, so that it's one-to-one, then y equals 4x squared minus 3. Add 3 to both sides, we get y plus 3 equals 4x squared. Divide by 4, we get x squared equals y plus 3 over 4, and square root it. So now we've made x the subject, and then we're going to replace x with f to the minus 1x and y with x. So another important thing you need to know about functions in inverses is that on a graph, the inverse is the reflection of the original in y equals x. So my yellow line on the graph is half of a quadratic. The blue line that I've just put in is y equals x. And so to reflect it, I tend to try and do it in parts. So I pick one part, reflect it, then pick the other part. You'll pick up your own way of actually doing that.